Okay, now we're going to start talking about irrigation system auditing on section 7. So our learning objectives: understand the reasons for conducting an irrigation system audit. Number 2, have a basic understanding of the terms distribution uniformity and irrigation efficiency. They are different, so we do need to learn the difference. Have a basic understanding of the terms precipitation rate and matched precipitation rate. Know how to determine the precipitation rate. 5, understand tools required to conduct an irrigation system audit. 6, understand how to conduct an irrigation system audit site evaluation. 7, understand how to conduct an irrigation system audit tune-up. 8, understand how to conduct an irrigation system audit test for overhead spray, and also understand how to conduct an irrigation system audit test for drip irrigation. So we're going to begin with the purpose of irrigation system auditing. So the purpose of an irrigation system audit is to assess how effective an irrigation system is at applying water to a specific hydrozone. The results of an irrigation audit can be used to develop an irrigation schedule for the hydrozone tested. An accurate irrigation schedule helps to ensure that water is used as efficiently as possible within the limits of the irrigation system. And that's ultimately what we're trying to do, right, is to use water as efficiently as possible, save our resources here. So observations made during the audit can be used to suggest system improvements, and optimizing irrigation system performance helps improve the efficiency with which the water is applied. So we're looking for efficiency and looking for ways to make sure that the water that we are distributing is getting put onto the hydrozone as efficiently and effectively as possible. So distribution uniformity and irrigation efficiency. What's the difference between these two terms? Well, distribution uniformity, or DU, is a measurement of how evenly the water is applied to a hydrozone. It's a value between 0 and 1.0, where 1.0 is perfect uniformity. In reality, our irrigation systems are never going to operate at a 1.0. It's always going to be a value less than 1. Irrigation efficiency, i.e., is the ratio of the volume of water that is beneficially used by the plants in a hydrozone to the volume of irrigation water applied. So let's think about that again. It's the ratio of the volume of water beneficially used by the plants to the volume of irrigation water applied. If there was 100% efficiency, it would mean that all the water that is applied is used directly by the plants. That's not likely either with our irrigation system. For that case, for irrigation efficiency, a lot of the water could be used inefficiently due to runoff. If we're overwatering with those fixed spray heads that are putting out a precipitation rate much higher than what our clayey soils can take on, we're going to get a lot of runoff. That's obviously not water that's going to be beneficially used by the plants. Situations like that. DU and IE are different metrics. DU and IE are different metrics. Looking closer at distribution uniformity, a high DU is desirable because it allows the entire root zone to be irrigated sufficiently and evenly. It also helps ensure adequate plant health. If DU is low, it's necessary to overwater or underwater areas of a hydrozone due to the uneven application of water. Okay, so here's a picture of poor DU, poor distribution uniformity. Again, it's the uniformity. How uniform is the water laid down? So this is considered excessive irrigation, and you can see this part, this line here, the dashed line is where the root zone of the plants are. That's where we want to target our watering, right? We don't want our water to go beyond that root zone. We want our water at the root zone. Anytime we're watering beyond the root zone, as in this case, we have excessive water. And you can see, because there's more water coming here and then there's less water coming here, that it is not uniform. Uniform application would basically mean that the water is all at one level. So in this case, we're overwatering the entire area. And the water, any water that's moving beyond that root zone is lost to deep percolation. So here's another picture of poor DU, and this is insufficient irrigation. Again, dotted line is the root zone. That's where we want our water. On this part of the diagram, of course, it looks like it's watering okay, but then we have insufficient watering here. So insufficient watering of some areas will result in dry spots. So that's where you see kind of those little crop circle formations that we saw in the first picture. Because this will be a dry spot and the grass will dry up here in this area, whereas this area, the grass will be nice and green. So that causes those crop circle images. Here's an example of the crop circles that you might see. Irrigation efficiency differs from DU because it takes into account other factors such as overspray, runoff, and the runtime of the irrigation system. A system with a high DU might have a low IE due to overspray. A system with a high DU with an application rate much higher than the soil can take will have a low IE. A high IE does not always result in a healthy landscape since it can be achieved by underwatering. And what we mean by that is a high IE can be achieved by underwatering because more of the water applied is going to be beneficial because there's less water applied. So you have to look at all these factors when comparing IE and DU. So here's irrigation efficiency examples. So at the top here, you see a good distribution uniformity. And again, it's uniformly applied, but it is excessive watering. Again, we're trying to water at the root zone. We don't want it to lose water to deep percolation. So this is poor IE. Hydrozone with good distribution uniformity, although it's excessive, but poor IE due to the overwatering resulting in water being lost to the deep percolation. So again, that irrigation efficiency is that ratio of the volume beneficially used by the plants to what is being applied. A loss beyond the root zone is not going to be beneficially used by the plants, so therefore a poor IE. So here's what we ultimately want to see is a good distribution uniformity and a good irrigation efficiency. So the hydrozone with a good DU and IE as the water manager is irrigating to the proper depth. And it's not only proper depth, but it's being applied uniformly. So that's going to provide a good distribution uniformity and also a good irrigation efficiency. Typical distribution uniformity values, and this is important to know also for the exam. So drip irrigation has about the highest, which you would kind of make sense because we are applying drip irrigation very specifically to the root zones of the plants. It's at a lower pressure than other irrigation. So their distribution uniformity is between 0.8 and 0.95. Remember, distribution uniformity is 1.0, usually less than 1.0. 1.0 is considered to be a perfect system, and there are no perfect irrigation systems out there. You could also think of this as like it being 80 to 95% efficient, and another way of looking at it. The DU for rotating sprinklers, 0.55 to 0.85, that's about the same as rotors, 0.55 to 0.85, but our spray head sprinklers have a low DU, 0.45 to 0.75. That's at the highest end of the range. At 0.75 is pretty good for spray sprinklers. These values in the table are pretty much general guidance. This is kind of like the range that we see things, but the only way we can get accurate measurements is by actually doing an audit to obtain the actual values. Because, let's face it, landscapes and irrigation systems can be complex. They can be laid out in complex ways. So in order to get real true values, we actually have to measure them during an audit. And it's also important to know that certain irrigation devices inherently apply water more evenly than others. Drip irrigation will always have higher DU than spray sprinklers. Head-to-head coverage. So overhead irrigation devices are designed to have overlapping coverage as the spray pattern of individual sprinklers are typically not uniform in their entire diameter of throw. So we like to say that this head, this is the spray head, is actually spraying to water this one, and this spray head is watering this one. So that's why it's called head-to-head coverage, because this spray head is watering this one, and that one is watering this one. So we need to have head-to-head coverage to get the most uniform coverage. More overlap might be required if there's an issue with wind. So if you have a landscape that's in an area of prevailing wind, then wind might be an issue, and you might have to have more overlap between the heads. So a head-to-head coverage is usually more easily achieved like in a sports field or a big rectangular area or a square area, where other areas like curvy, shapy things, it's going to be harder to do head-to-head coverage there. And also overhead irrigation devices such as sprinklers, they are designed to have overlapping coverage as the spray pattern of individual sprinklers are not typically uniform for their entire diameter of throw. Head-to-head coverage of sprinkler spray patterns is typically used to determine optimal distribution uniformity, or DU, by ensuring that the spray of one sprinkler goes all the way to the next. Any deficiencies in coverage are smoothed out. Figure illustrates the spray pattern for two sprinklers with head-to-head coverage. When wind is considered an issue, sprinklers should be placed even closer, perhaps as much as 45% of the diameter of throw. Whenever possible, try to use drip irrigation in high wind areas so that we have less evaporation and overspray as a result. You'll have more direct application to the plants and their root zones by using drip as opposed to doing spray heads with excessive wind. Here are some pictures of causes of poor DU and irrigation inefficiencies. So the leading causes of poor distribution uniformity and irrigation efficiency include improper head spacing. So we have a head spacing that's less than the head-to-head spacing we were just talking about. Mismatched nozzles resulting in uneven application. They might be from different brands. You might go out there and find somebody stuck in a nozzle from a different brand, or they're not matched according to the distance, so the rate of throw is different. Water pressure could be too high, causing misting. We talked about before about tuning a valve, or it could be too low, resulting in the reducing the radius of throw. Of course, we could have overspray, again, wear and tear of the irrigation equipment over time without proper maintenance. Things do break and crack. We could have clogged heads or nozzles, broken or missing heads, tilted heads or heads below grade. Spray patterns could be blocked by hardscape features or plant material. Leaking seals, missing emitters, and severed drip lines. These are all causes of poor distribution uniformity and irrigation inefficiency. Precipitation rate and matched precipitation rates. We want to have an understanding of these terms. This is an important concept also for the exam. We want to know about MPR and PR. So there's a couple of different types of precipitation rates. There's gross precipitation rate, and then there's net precipitation rate. Precipitation rate is the rate at which water is applied, measured in inches per hour. Gross precipitation rate measures the total flow of the hydrozone. The net precipitation rate measures only the water that is effectively applied to the hydrozone landscaped area. The difference between the gross precipitation rate and the net precipitation rate are water losses due to factors such as leaks, overspray, runoff, and wind drift. And you can actually calculate the gross precipitation rate based upon manufacturers' catalogs and also by the use of a water meter to get the flow rate of the hydrozone as well. So when we go into scheduling irrigation controllers, know that the precipitation rate is going to be a key input in determining the irrigation schedule that we need to calculate. So this table shows some of the typical precipitation rates or PRs of different emission devices. So this needs to be related to your soil infiltration rate. That's why knowing about your soils is really important, because you don't want to have a precipitation rate that's higher than your infiltration rate. Otherwise, you're going to be having a lot of runoff. Be familiar with these precipitation rate for these application devices. So fixed spray rotors always has a high precipitation rate. And for our clay soils here in Arizona, too high for what we have to work with. Rotating sprinklers, much better for our environment, 0.4 to 0.6 inches per hour. Rotors, 0.25 to 1.5, so they can have a higher precipitation rate or a lower precipitation rate. Inline drip, 0.1 to 2.0 if it's set up in a grid. So inline drip, even though we tend to think of it as low volume, slow precipitation rate, if it's in a grid setup, it can have a high precipitation rate. So do note that. Typically, we think of drip irrigation as low flow, low volume, low pressure. However, you can have a high precipitation rate if it's in a grid type system. Point source drip It depends upon the emitter placement. Low flow bubblers depends upon the flow rate and the wetted area. It's important to know the precipitation rate of each hydrozone in order to be able to properly determine the irrigation runtime and to program your controllers based upon that. So match precipitation rate. So it's important to understand the difference between match precipitation rate and just regular precipitation rate. So when the precipitation rate is matched, the flow rate increases as the arc increases. And when the precipitation rate is not matched, the flow rate remains constant. Emission devices that do not have matched precipitation include rotors and older fixed spray sprinkler nozzles. When you're working within a hydrozone, you want to make sure that the precipitation rate of individual emission devices is matched to ensure an even rate of water application. So the table provides an example of a matched precipitation rate, MPR rotating sprinklers. When the precipitation rate is matched, the flow rate of the emission devices increases as the arc increases. So the flow rate of the 180-degree head is double that of the 90-degree head. You can see that here. So here's the 90-degree head, here's your flow rate, and when you get to the 180, it's double. So as the arc increases, the flow rate increases, but the precipitation rate stays the same. That's what the match means. It's matched. Precipitation rate is the same across all these different arcs, the spray heads. So the precipitation rate is matched and it stays the same, but as the arc of the spray head increases, the flow rate of it increases in proportion. When the precipitation rate is unmatched, the flow rate of the emission device remains constant as the arc increases, and you can see that here. So our arc is increasing, 90, 180, 270, 360. So as the arc increases, the flow rate all remains the same, but the precipitation rate actually decreases. So it goes from 2 down to 0.5. The precipitation rate of the 180-degree head is half of that of the 90-degree head. The precipitation rate of rotors can be matched using different nozzles depending upon the arc rotor. Alternatively, rotors with different arcs can be grouped together on separate irrigation valves with different run times, like for example having 90-degree rotors on one valve or valves and only 360-degree rotors on a separate valve or valves. If you find older spray heads don't have matched precipitation, they should be retrofitted with the new matched or MPR sprinklers, preferably the high efficiency rotating ones. All right, so how do we calculate precipitation rate? Gross PR manufacturer specifications. So similar to what we learned about in section 5, we can use the manufacturer specifications for both overhead sprays and drip lines. So we can look up the gross PR of a hydrozone. It's necessary to know some specifics about the emission device in order to look up the precipitation rate. So we need to know the brand, we need to know the model, we need to know the nozzle, we need to know the static water pressure and spacing pattern and dimensions. These are all things we need to know to figure out what the gross precipitation rate is. Going back to this chart that we saw in section 5, this shows an example of performance specifications for overhead emission devices. This is the Hunter MP rotator. So here's MP 1000, MP 2000, MP 3000. So the flow rate and precipitation rate vary by the radius of flow and the static water pressure. So here's your water pressure here. Here's your arc. So water pressure and the radius of throw is here. So manufacturers typically publish the precipitation rate for sprinklers laid out in a square pattern and in a triangular pattern. The actual precipitation rate will vary due to factors such as differences in how the system is laid out, changes in system pressure, overspray, and wind drift. Gross PR for manufacturer specifications. This is for the Netafim Techline CV precipitation rate. So this figure shows an example of performance specifications for drip line, the Netafim system. Manufacturers typically publish the precipitation rates for drip line laid out in a grid. And it's going to vary by the emitter flow, the emitter spacing on the drip line, and the lateral spacing of the drip line. The flow rate and the precipitation rate of most drip lines should be constant at different pressures within the range published by the manufacturers. However, the actual precipitation rate will vary due to differences in line spacing in the field. Looking at the chart again, as we said, the precipitation rate varies by the emitter flow rate and the emitter spacing and the lateral spacing. So here's your emitter flow rate for this grid system. You can see it's different across the different types of applications. There's a turf application. Here's shrub and ground cover applications. Here's your emitter flow rate. And then the spacing. So again, we have like a grid system. So a spacing between emitters, 18 inches, 12 inches, 12, 12, 12. Here's 18, 18, 12, 12. A lateral row spacing. So remember, this is a grid system. So from one row to the next can be 18 inches, 20, 22, or as little as 12, 14, 18. The precipitation rate does vary based upon all these things. It varies based upon the emitter flow rate, the emitter spacing on the drip line, and the lateral spacing of the drip line. But most drip lines should be constant at different pressures within the range as specified by the manufacturers. But it's going to vary a little bit due to the differences in line spacing in the field. Flow rate formulas can be used to determine the gross PR of a hydrozone. In order to use these formulas, it's necessary to know the total flow of the hydrozone. The most accurate method of determining the flow of the hydrozone is to measure it using a water meter. So you want to activate the system to remove any air from the lines, take a meter reading, and then allow the hydrozone to run for a certain amount of time, like 5 minutes for spray or 10 minutes for drip. Go out and take a second meter reading at the end of that time. If the meter reading is in CCF, first convert to gallons by multiplying by 7.48. The flow rate is the number of gallons delivered divided by the runtime in minutes. An alternative method is to look up the flow rate of the emission devices installed using manufacturer's specifications. So what you're going to do is sum the flow rates of the individual emission devices to obtain the flow rate for the entire hydrozone. If it's a drip system, convert the drip emitter flow rates from gallons per hour to gallons per minute by dividing the flow in gallons per hour by 60. So this is a general formula for spray and drip irrigation. So it's the precipitation rate equals 96.3 times the gallons per minute over the hydrozone area. So the GPM equals the flow rate of the hydrozone in gallons per minute. Hydrozone area is in square feet. 96.3 is a constant conversion factor, so it's always going to be in there. It helps convert the square feet and gallons into inches. Okay, and then for the drip line laid out on a grid, so that NetFM system, you're going to have precipitation rate equals 231.1 times the gallons per hour divided by the emitter spacing and the row spacing. So precipitation rate equals the gallons per hour times 231.1. And that's going to be divided by the emitter spacing times the row spacing. Now, there's no need for you to remember the formulas. The formulas you will be given on the exam. You do need to know how to apply them and what they relate to, but you don't have to remember the exact formula. So here's a precipitation rate calculation example. So we've got a square hydrozone measuring 28 by 28, irrigated with the Hunter MP rotators, which are matched precipitation rate, operating at a operating pressure of 40 psi. So in this case, we've got 4 90-degree heads here on the corners at a flow rate of 0.21 each. We have 4 180-degree heads with a flow rate of 0.42. So there's one here, one here, one here, and one here, and then one full circle one in the middle. To get our flow rate, what we do is we add them all together. So we got 4 times 21 is 0.84, 4 times 0.42 is 1.68, and then 1 with a 0.48, you add those all up, and so we know that our flow rate for that hydrozone is 3.36 gallons per minute. Our area is 28 by 28, or 784. So then we take all that, plug it back into our formula. So 96.3 times our gallons per minute, which is the 3.36. And we're going to divide that by the 784. We get 323.57 over 784, and it's 0.41 inches per hour is our precipitation rate for this zone. Let's talk about drip line then. So Here we have a rectangular hydrozone measured 30 by 60, irrigated with the Netafim tech line laid out on a grid. 0.4 gallons per hour emitters, 18-inch emitter spacing, 18-inch row spacing. 0.4 gallons per hour is a nominal flow, and the actual flow is 0.42. So if we got a nominal flow and an actual flow, which one do you think we should use in the formula? Yeah, that's correct. We should use the actual flow rate in the formula. If we know the actual flow rate, we should use it because the nominal flow rate is going to be part of the manufacturer specification, which if we have real data, we want to use the real data. So here's our formula. So it's a 231.1 times 0.42, which is our flow rate. And it's over our emitter spacing and our row spacing. So our emitter spacing is 18 inches and our row spacing is 18 inches. So we get 231 times 0.42 is 97.06. Divide that by 18 times 18, which is 324, and you get 0.3 inches per hour. Okay, the best way to determine precipitation rate is by doing a catch can test. That's the way we do net PR with the catch can test. The reason it's the preferred method for calculating PR is it only measures the water effectively applied to the landscape hydrozone area. It does not take into account any of the water loss due to factors such as leaks and overspray. And later in Lesson 8, we're going to be going over how to perform a catch can test in more detail. Irrigation system audit tools. Of course, there's a number of different tools we're going to be using to do our irrigation audit. Some of the first ones are the actual catch cans, and there's a variety of them out there. The common ones are Cal Poly's, ITCR, DWR. Texas A&M have some that are measured in milliliters and inches, and Utah State University has some that are measured in milliliters, inches, and centimeters. The ones that we have here that I'm using are the Texas A&M ones, which are these catch cans here in the image. Some of the other tools are flags. So when we go out and turn on the system, we're going to flag all the heads. If we are going to be measuring rotors, then we'd use a pitot tube to get the pressure. But on spray heads, we have a digital gauge that we use, pressure gauge on a T. We're going to put those on the spray heads at the beginning of the line and at the end of the line. We have a soil probe, which we're going to use to take a soil probe sample in a number of areas. We're going to check not only the type of soil, but also how far down the roots have grown. This is a device to change the configuration of the rotors. Measuring device for measuring the area that we're going to be checking. You can also do this digitally, which we'll talk about. There's an anemometer. It took me forever to learn how to say that, but that is our wind speed gauge. Of course, we're going to need a calculator, probably a screwdriver, a clipboard, stopwatch, cameras on our cell phones. These are some of the tools that we need during our irrigation audit. Irrigation audit, evaluation of a site and irrigation system. So we want to understand how to conduct an irrigation site audit and evaluation. Ideally, we're going to have an understanding of the site and the irrigation system being evaluated. Each area is going to be different, and so we want to make sure we have as much information as possible. It's also important to understand the goals of the audit. The audit's basically a service that's being provided to the client, so both parties need to have an understanding of what's to be expected. And before you go out there to do your audit, you want to obtain as much information as possible about the site being audited. Often, time spent preparing for an audit in advance can actually save you more time in the field. So it's helpful to get information before you get out there. If you can get the as-built information, the as-built plans on the site, that's great. Not always possible, though. But even if you can get the basic landscape irrigation plan, that's helpful. Any aerial images, water use records. We have information on the plant material that's already out there. Information on microclimates, soil types, any of the slopes. Should do a visual inspection of the irrigation system from the water meter to the emission devices and to the controller. So just a quick look around the area can provide the auditor with a significant amount of information with respect to the condition of the system before you even do the audits. It's helpful to gather as much information before you go out to do the physical audit as possible. This is all part of your initial site evaluation. So when you are on site, you want to activate each hydrozone and observe any issues that might impact the system performance. The whole purpose of activating the hydrozones is to quickly check the overall condition of the system. Irrigation issues should be noted and either resolved during the system tune-up or noted in the audit report. Explain that by making an inventory of existing issues can be helpful to build a case for repairs and upgrades. So the more issues you can note, if things are really out of whack, it's helpful to record those so that you can encourage the owner to make proper adjustments. You want to take photographs of the system components and any of the issues that you find for future reference and also for future audits. So you can kind of go back in time and say, hey, has this thing been a problem for a long time or is this a new problem? And you want to highlight that in photographs. And it's a great way to communicate them to the client and also to anybody who's going to be going out there to fix the actual issues. If there is sufficient information, determine an approximate water budget for the site that can be compared to water use records and also can be used to calculate the cost savings that might be expected from irrigating more efficiently or performing system upgrades. An auditor can usually request water use records prior to conducting an audit on an existing site and then use this data to compare actual water use to a budget. This practice allows the auditor to begin the audit knowing whether the landscape is receiving a surplus or a deficit in irrigation. All right, so let's talk about irrigation system audits and irrigation system tune-ups. So we want to understand how to conduct an irrigation system audit tune-up. So depending upon the parameters of the audit being conducted, it can be beneficial to perform a basic system tune-up prior to proceeding with the system testing. This kind of goes back to the agreement that you've made with the client. The way I would define like a system tune-up is just kind of going out there, turning everything on and checking it out, see if there's things that can kind of be snuffed up before you actually do the audit. You don't want to run the audit if there are simple things that can be done to adjust things like the spray heads or something as simple as maybe changing a nozzle. You want the audit to look as good as possible. But if the client doesn't want to pay for that, then you just need to go ahead with the audit. Again, it depends upon the goals and parameters of the audit. New landscapes, you should look for installation issues. Everything should basically be operating within specs. For new landscapes, a system tune-up really shouldn't be necessary, but the auditors should look for elements of the system that might be missing or not installed properly. For example, ensure that drip valves have a filter and a pressure regulator installed. That could be one thing. Existing landscapes, the auditor should use judgment to make small adjustments. Caution should be used not to damage the system components, especially older systems where components might be corroded or brittle. So you want to check for water pressure, clogged nozzles, heads, spray heads that are out of alignment, plant material blocking any spray heads, missing emitters, issues that can't be easily rectified, and then you must decide whether or not to proceed with the system testing. Will testing provide useful information if everything's completely out of whack? Probably not. If you can just do a few quick tune-up-y things to get ready to do an audit, that's great. But if it's going to be kind of a shovel-ready moment where you actually need to start digging and moving things around, then it might not be in your best interest to do an audit at that point in time. Irrigation system audit, irrigation system testing, and overspray. So we want to understand how to conduct an irrigation system audit test for overhead sprays. These are some of the forms that we're going to be working with. It's a copy of the QWEL Irrigation Audit Exercise form. I really like how they set up these forms because it walks through the formulas step by step, including the scheduling. It's a great form and it's an easy way to kind of understand what you're doing. So what we're generally going to do is you're going to complete pages 2 to 4 in the second column of the table on page 5 in the field. And we're going to complete the distribution uniformity and the PR calculations in the classroom, make sure we all have the same data. And then we're going to make sure that everybody completes the rest of the calculations independently. So in other words, we're going to be going out into the field getting all the data. We'll make sure everybody has the same catch can volumes and data. We'll calculate the PR. Then the rest of the recommendations and things on the last page are going to be up to you. Those are going to be all done independently. So what are the first steps? We're going to diagram the area. We're going to draw a diagram of the test area, including the overall dimensions, the head locations, the head spacing, the catch can locations. We want to measure the wind speed using an anemometer. We're only going to proceed if the wind speed is less than 5 miles per hour. We do want to check it a few times during the audit itself. The wind zone to be tested needs to have the spray bodies marked with flags. So usually we go out there, we'll turn on the system, and we'll go out and we'll mark all the spray bodies with flags to start. Once we get a good idea where all the spray bodies are, we're going to place the catch cans in the zone to be tested. We need to have a minimum of 24 catch cans. Regardless of how many we end up using, the number should be divided by 4. Ideally, we want to leave about 2 feet between the spray body and the catch can. And we want to lay the catch cans out in a uniform grid. So you want to space the cans approximately 5 to 8 feet on center for fixed and rotary spray sprinklers, and to space the cans approximately 10 to 20 feet on center for all rotors. So before you actually do the audit, you want to make sure you pull all the flags before running the test, as they could obstruct the path of the spray. Next, we're going to run the test and record the results. So we're going to run the irrigation zone for a sufficient amount of time to collect a minimum of 20 milliliters in the catch cans. For a typical manufactured catch can, we want at least 20 milliliters. Typically, it's 5 to 10 minutes for a spray, or 10 minutes plus for rotors. We want to measure and record the amount of water in each catch can. So ideally, use the milliliter scale on each catch can. If no scale is available, you might have to pour the water into a measuring jug or graduated cylinder. For catch cans with straight sides and a flat bottom, simply measure the depth in inches using a ruler. Ensure that the catch cans are numbered on the diagram. All right, well, here's the formula for the distribution uniformity low quarter. You're taking the average catch can volume of the low quarter, and you're dividing it by the average catch can volume of all the cans. Same thing if you're doing the depth. If you're measuring in inches and you're taking the average catch can depth low quarter, the average catch can depth of all cans. Typically, it's the volume. So average catch can volume of low quarter is determined by summing the volume of water in milliliters in the low quarter and dividing it by the number of cans in the low quarter. The low quarter is 25% of the catch cans with the lowest volume of water. If you have 24 cans, then you're going to be looking for the 6 cans with the lowest value of water. If you have 40 cans, then you're going to be looking for the 10 cans with the least amount of water. You're going to average the catch can volume by summing all the volume of water in milliliters and then dividing by the total number of cans. The first one, you're going to get the average of the catch cans for the low quarter, and then you're going to divide it by the average catch can volume of all the cans. It sounds more complicated than it actually is, and we'll be going through different examples as we move forward. The precipitation rate net formula, if you're using volume in milliliters, precipitation net is the average catch can volume of all the cans that you just calculated in the other formula, times 3.66, and you divide that by your test run time and your catch can throat area. So the average catch can volume of all cans is determined by summing the volume of water in milliliters in all the cans and dividing by the total number of cans. Your test run time is measured in minutes. Your catch can throat area is measured in square inches, and 3.66 is a constant to convert milliliters to cubic inches and minutes to hours. If you're going to do it in depth in inches, then this would be the formula. So it's average depth of all cans times 60 divided by your test run time. So let's do an example. Here's some actual catch can data. Okay, so these are the actual results. So what I want you to do, so there's 24 catch cans. So we said the low quarter would be the lowest 6 catch can volumes. Taking a look at these values here in the milliliter column, what are the 6 lowest values? Let's do this together. It's kind of easier to start from the bottom. So the 20s, we need to have at least 20 milliliters in each one, right? So think backwards. What values do we have in the 20s? Well, we have a 25 and a 27. I don't see any other 20s. And we can go up to 30s. So that was 1, 2. We need 4 more. So what's our lowest in the 30s? Well, here's a 30. Here's another 30. So that brings us to 3, 4. So we need 2 more. And then what's our next lowest in the 30 category? Well, here's a 34. And then here's another 34. So what do they show us for our results here? So we got a 30, 34, 30, 25, 27, and another 30. So that's exactly what we were just talking about. So we add all those low volumes up. And that is 176. If we add up 30, 27, 25, 30, 34, 30, should come up to 176. Divide that by 6 to get the average, which is 29.33. The total volume for all of the cans, so we're adding up all the milliliters for all the cans, comes out to 1,045. We divide that by 24, and then we get an average of 43.56. To get our distribution uniformity, we divide our low quarter by our total average, the average of the total number of cans. So 29.33 divided by 43.54, and we get a DU of 0.67. Our precipitation rate uses some of this data. So our precipitation rate is the average catch can volume of all the cans. So here's our 43.54 is the average catch can volume of all our cans times 3.66. So that value comes out to 159.36. And we divide that by our test run time, which was 20 minutes, and our catch can throat area, which was calculated to be 16.25. So you divide the 159.36 by the 20, which is the test run time, and then by the catch can throat area, which comes to 325. So that value is 0.49 inches per hour. So section 9, irrigation system audit. Irrigation system testing for drip irrigation. So we want to understand how to conduct an irrigation system audit test for drip irrigation. A little bit more complicated than for spray heads. So it's not really practical to test uniformity for drip irrigation systems. We tend to use a 0.9 value for pressure compensating emitters and 0.8 for non-pressure compensating emitters. This is just something you need to remember. But the focus on the site evaluation and pressure testing, we do want to measure pressure at the beginning, mid, and end point of each zone. And if there's a variance of greater than 20%, then we need to do some additional investigation. Okay, there's essentially 3 different ways to take pressure readings on drip line. So one is to insert a gauge fitted with a pitot tube into the tubing. You can do that in multiple areas to make it more efficient. And then after you get done with the test, you need to goof plug those holes. Another way is to use a pressure gauge fitted with a 1/4 inch tubing for point source emitters with a barb fitting. So pressure gauge fitted to a 1/4 inch tubing can be attached to 17 millimeter drip line using a Netafim emitter microtubing adapter. Or a third way is use a pressure gauge fitted with a rubber tip that can be placed over emitters to get a pressure reading. So in this case, it's a 1/4 inch FIPT times 1/8 FIPT brass bell reducer. And then you put it over an 1/8 of an inch MIPT air compressor blowgun tip. And then you can put that rubber tip over the emitters to get a pressure reading. So you can determine the gross precipitation rate using the general formula for point source drip or the PR formula for drip line laid out in a grid. Determine the flow rate using the flow test, which is a water meter, or the manufacturer's spec. So that's going to sum the flow rate of all emitters in the hydrozone. The hydrozone area should only include the wetted area. For point source drip, estimate the wetted area by the percentage of the hydrozone area that received irrigation by summing the estimated wetted area per emitter. And it all depends upon the flow rate and the soil texture. Drip irrigation auditing is a little bit tricky because there are several issues that an auditor might encounter when determining the precipitation rate of a drip hydrozone. One of them is accurately determining the wetted area for a point source drip system versus, looking at drip line laid down at a grid. The precipitation rate of a drip irrigation system should be determined using the general precipitation rate formula for point source drip or using the PR formula for drip lines set out in a grid. When determining the application rate of a drip zone, the auditor can either perform a flow test using the water meters described in section 4.2 or look up the flow rate of the emission devices installed in the zone. But be careful to only include the area within the hydrozone that would be receiving irrigation in the precipitation rate calculation. Non-wetted areas should be removed from the precipitation rate calculation. Determining the wetted area is relatively simple if the hydrozone is irrigated with a grid of drip line, but more complicated if drip irrigated with a point source drip. For point source drip, there are several different approaches. One is to estimate the percentage of the hydrozone area that receives irrigation. Another is to estimate the wetted area per emitter, and then sum them for the hydrozone. The wetted area for each emitter will depend upon the flow rate and the soil texture. So it gets a little bit more complicated. You don't need to perform an audit on drip irrigation to receive your QWEL certification. It's not part of it. All right, finally, we're getting to the irrigation system auditing review questions. So there are 12 here. Make sure you know how to answer these in detail. Know the difference between DU and IE, precipitation rate that is matched and unmatched, net PR, gross PR, all these things that we covered. Make sure you know these in detail. And we'll see you back for the next section.